Hello friends, I would like to make this video uh, about connecting the Tower of Hanoi puzzle, how this puzzle is connected to mathematical function. So let me go straight away. When you want to transfer the number of disks from one peg, so can you see this? You have to move it either here or you have to move the third one. So this one shows only begins with two disks. What if there was only one disk? So all you do is just move over here, right? That will take just one minimum step. So I use the two columns here. The first column stands for how many disks are you putting in the first peg, and the second column is minimum number of moves, so or steps. So I use the uppercase M stands for the minimum number of steps needed, and lower M stands for how many disks that I place. When you move this, there's one condition is you can't put the bigger disk on top of the smaller one. And you can do only one at a time, one move at a time. So let me start with first one. If there was just a single disk, then it would take only one minimum step, right? Because you just have to move it to another one. Now I have two disks here because this simulation shows with the help of it starts with 2. So watch it out. So if there are two disks, then how many steps, minimum steps needed? So I click here, there you go, 2, 3 steps, see, and you're done. Right? So that means if there are two disks, it needs 3 minimum steps. Let's change it to 3 disks. So first, move this right here, 2, 3, 4, 5, 6, and 7 steps. So that means if there are 3 disks, the minimum moves or steps needed is 7. Now remember, let's change it to 4 disks. Now for 3 disks, you use 7 minimum steps, right? So if there are 4, question is you can pause the video and see, can you figure it out without playing the puzzle. So remember again, 3 disks, when you move, it took us 7 steps. And if I change this to 4 disks, then how many minimum moves needed to move this whole thing? So you can pause the video for a while, check, and here you go. Let me make sure. So now this is a small one. I want the whole thing. You can move anywhere, doesn't matter, as long as I want to move those 3 over this side. So click here. Sorry, this one I'm getting 2, then 3, then 4, 5, 6, and that's what we did before. Now, this is that additional disk that you have to move here, one additional move. Now you begin, we have to move back those 3 disks on top of this. So we have to use another 7 steps. Remember, we started with 7 steps, then we moved this one additional and then go back. So let's do that. So put this here, place this one here, put this one here, put this one here, bring the smaller one on the right, and you can see it takes 15 moves. So if it is 4, it is 50. So, and you see the pattern there, every time whatever number of moves are there, disks are there, all you need to do is, you are doing the top, leaving the bottom one, you just see the one before. Let's go check here. So we need to write, one is recursive definition. So first thing is recursive. So let's see, what is a recursive? How can we write recursive definition for this puzzle? Okay, so in the beginning, so when there was a one disk, that means when n is 1, so minimum number of steps for this was just the 1, because you have to just move it. But then after that, you will notice there is kind of there is a pattern there. And you can see from this step to this step, it is 2 times. How do we get? It is 2 times the previous step, that is 1. So it is previous f and plus 1 again. So it is 2 times 1 plus 1. How do we, so that means the next one is, again you can see the pattern, 2 times 3, so you just double this 3, so it is double. So I'm using the red color here. 2 times the one before, that is 3, which is 3 and plus 1. And now that plus 1 is when you're moving the bottom disk, that's one additional. And this means you're using the, when you move the top disks, so the minimum steps is 3, let's say. So you do it twice, that's why it is twice. Then again, right here, it will be 2 times the previous, that is 7, and then plus 1, which is 15. How do we get the next one? Will be 2 times 15 plus 1, and you can check that it's going to be 31, so put a 31, and that's like one more. 2 times 31 plus 1 is 63. This is 63. So the question is, can we write recursive definition? Yes. So every time you double the previous one and add 1. So here, that means at any step, this is for n equals 1. What about n equals 2, 3, 4, 5, which also means, what about when n is greater than equal to 2? That means number of moves needed to move n number of disks is twice, look at this, this is like twice the number of moves in the previous. That means this is m is 1, this is n is 2, this is m3, this is m4, and so on, right? So at any time, the number of, let's say 31, is always the one before, n minus 1. So this 4 is n minus 1. So if it is n, this is n minus 1. And plus the very first one, you see that same thing? So plus 1. And that's it. So the first one is, you needed, this is the main one, is that you need the first step for a single disk to move, you need 1 step, and then after that it just continues twice this and then plus 1. And that's all. This is the recursive definition. The question is this arithmetic sequence and geometric sequence? So we are not adding the same thing every time, or you're not multiplying the same thing. None of neither arithmetic sequence or geometric sequence. But then, can we write explicit? So this was the explicit definition. Sorry, recursive. Now we need to know what is the explicit definition, or you can say nth term. Without using the previous, but using the very first one. Using the first one, how do these numbers show up? Let me show this part. So I want you to pause the video for a while and see if you can figure out yourself. Check these numbers. Are this number connected to anything strikes you, maybe this 1, 3, 7, 50. Our goal is using the first one, this 1. Think of perfect squares. So what are the perfect squares? 1, 4, 9, 16. These are the perfect. Can you think of these numbers and are they connected here? And you say yes. This 3, this could be perfect square is one thing, but can you think? I'm sorry, I should have using exponential. What's 2 raised to 1? What's 2 raised to 0? What's 2 raised to 3? 2, sorry, what's 2 raised to 3? What's 2 raised to 4? 2 raised to 5. So anything connected, these numbers are related to that. You can see that, let's begin as 15. So this 15 is 1 less to 16, that is 16 minus 1, right? This 31 is 32 minus 1. This 63 is 64 minus 1. This 7 is 8 minus 1. And you can see the pattern there. This 3 is 4 minus 1. And this one is 2 minus 1. But what does this 2, 4, 8, 16, 32, and you can see those numbers are these numbers. This becomes 2 raised to, if there is a 1 here, let's see if this is the, okay, I already used blue color 1. So this is 2 raised to, so it is 2 raised to 2 raised to 1 minus 1. Look at that pattern. This 4 is the same 2. So let me use this 2, red 2 square minus 1. This 8 is 2 raised to 3 minus 1. And you can see the same pattern, and finally you already know the answer, but I'm going to organize this. So this is 2 raised to 4 minus 1. This one is 2 raised to 5 minus 1. And you already know what I'm concluding. So whatever the step number you have, the input 1, 2, 3, 4, 5, they go as an exponent to the base 2. So the main number uses the base. So that's because 2 raised to 6 is 64, because you're multiplying 2 6 times. 2, 6 of them give you 64. 2 raised to 5 is 32, and you can see now you have an n. If it is n, so all you do is, if this input is n, just a variable, we don't know what n, it could be 5, 8, 9, 10, 11, 12. So the new function is n equals the base raised to the same n, the blue n, and minus 1 for n greater than equal to 1, because starts with n equals 1, 2, and so on, right? Hope it makes sense. So finally, so we get a beautiful function, and we know what is that function. This function is the exponential function. So this is exponential function with the domain with n equals 1, 2, 3, 4, and 5, and so on. So it's also called discrete function, because you can't have in between numbers like 2 and 3. It has to be 2, then 3. You can't have 2.5. So that's why it's also called discrete function. Discrete function. And the main thing is the exponential. Now, how does this look like? We want to graph it. We know the graph of 2 raised to x. 2 raised to x, the graph is this way. And what does that basically means is, the graph, if you see this as a minus 1, it is the original graph of the exponential function y. We know this is y equal to 2 raised to x, and then there is a minus 1. It means the whole graph moves one place down. That means if this point, if the horizontal asymptote that you see here, that is the y equal this one. So the main, this number that you see 1, 3, 7, they represent exponential function with the domain this, and the graph will look like something like this. So all I try to show is, let's graph it with the grid. So there it is. Let's check it out. I already have a grid. So when it is 1, it is 1. So if it is 1, this is 1. Then 2 is 3. 2 is 3 will be somewhere here. Then 3 is 7. 7 will be here. 4 is 15. That's 15. And 5 is 31. 31 is here. And 6 is 63, but I don't have it. I can easily make it right here. It goes this way. So if this is 30, this will be 60, and so on. 63 will be right here. So you get a graph. So this dot at 6 is going to be, and you can see it is almost like but you can't join the dots. But as I said, this is a discrete function where m n, the new function, is 2 raised to n minus 1. So that's it, you're done. But this is a subset of the exponential function. So if I want to graph the original function without discreting, if I have f of x equals 2 raised to x minus 1, which is with all the domain, then you see that the graph goes this way. So hope that helps to understand that in this so the main thing is the minimum number of moves needed to move the number of disks. The numbers are beautiful numbers, this 1, 15, 35. They are not just random, they are like representative of the numbers are part of the graph or the function, this one. So beautiful function we get exponential. I hope this makes sense, how beautiful it is to see how exponential function is connected to the Tower of Hanoi. This puzzle is being displayed at different places, games, or even the fair, carnival, and children play, but then the minimum numbers are this, and then that has a connection to the exponential function. I hope that makes sense. And you can see later on, as in the exponential function, as you go to the higher classes, we see there as limit for this function f of x, if an x approaches to a very large number, this f of x, I'm saying if the number of disks become bigger and bigger, then you see this becomes infinity, it's like unbounded. So if you don't, it just goes on. And the same thing is this, you can't have a 0, you can't have minus 1, but as we know for this function, as limit if your numbers will go on become very large negative numbers, then that is almost coming closer. There's a horizontal axis. So this one is that what I've drawn is this becomes equal to, this becomes almost closer. See that this graph approaches onto the line, dotted line y equals minus 1. So that's the horizontal, y equals minus 1 becomes the horizontal infinity, the horizontal asymptote. So this is horizontal. So a lot of information there not needed, but just thought of showing you how beautiful it is that minimum number of moves needed to move the disk from one peg to another peg is connected to this beautiful equation. That's the point. That was my goal for this video. Thank you so much for watching. Just felt to share my point of view. And the next video that I'm going to make is about checkers game. So the number of checkers. So how the puzzle on checkers is connected to another function called quadratic function. Okay. Okay, thank you.